faster than expected, and we are waiting for connection of the first speaker. And while probably if Professor Kordyuk already on site, he probably can start his presentation from the lecturer, from Professor Alexander Kordyuk, about the project of looking at quantum materials at training based on creation and new lab-based RPS techniques on site. Thank you.
So welcome again. I will just adjust some windows. Okay, so today I want to make such a complex presentation, which partially review and partially highlighted some of our results, and I called it now a synchrotron-based search for new quantum materials. And actually, this picture, you can't find synchrotron here, but it is somewhere nearby. It is just, I choose such a picture with association because it is made during one of our journey, let's say, near the Swiss light source when we measured when we did some experiment that was some break, and it is usual to spend time to walk into mountain. Therefore, this is just I choose association because it's mine. But close it. Okay. So thinking about this topic for me is many directional, and therefore it's difficult to make such a one line plan. Therefore, I just decided to speak, just choose my abstract and speak about electronic, about this terms which is here. So electronic band structure is a key quantity, and I want to speak about quantum materials, in particular about superconductivity, and actually about synchrotron experiments, which allows to measure this electronic structure, which defines all the property of quantum materials. And also to highlight one of examples of our research when electronic band structure helps to approach new quantum applications in superconducting electronics, and also highlight some of our ongoing projects which are related to these activities. So briefly, instead of motivating demonstration, I just want to show the slide. So it's about superconductors, superconductivity, which is, I would say, the best or classical, but still the best example of quantum materials. And their application, quantum applications, as we call it, electronic band structure, which is responsible for the whole business. And actually, this is I like this very much. Image of the Swiss light source, where a few of our participants here and organizer are now located. Okay, so quantum materials, if you want to know more about what is quantum materials or what is called now quantum materials, you can follow these papers in Chemical Review or Nature Physics, or just see the page in Wikipedia about it, which is quite nicely written. But in general, it is some quantum materials. It is now term like umbrella, which includes many materials. But people try to highlight or to stress the important phenomena as emergence, that all these materials, all materials are quantum, but in addition, there appear some additional from new, emerge new property, which makes them especially interesting. But I would use these words more strictly as material which lead to also quantum technologies or quantum applications. And Superconductivity, superconductors, as I said, it is classical example, and you know the bright applications about it, well known. This is international nuclear thermonuclear reactor experimental, which is building the most expensive up to now experiment. And this is Large Hadron Collider, where in both facilities about 1,000, I think 1,060 tons of superconductors used, mainly for superconducting magnets. And this application is really the most, as you know, this is magnetic tomography, yes, and some projects of using superconductors. Some time ago, people believe that soon all the cities became superconducting, but I would stress now about this application. This actually image represent the superconducting quantum computer. I will talk about it a bit later. But I wanted to start from the mechanism of superconductivity, because the mechanism is important to know, to design new materials, to understand, of course, the properties with the aim to design new materials and to discover new materials with better properties. And in case of superconductivity, it is believed that mechanism should help to discover superconductor, let's say room temperature superconductor. Although the mechanism of this BCS, which is Bardeen-Cooper-Schrieffer, suggested the mechanism for ordinary, let's say, superconductors, which were discovered long ago. And this mechanism was here, the emergent phenomena was that electrons interact and pairs with the help of exchange of phonons. And this phenomena, also this interaction, leads to opening of the gap in the electronic spectrum, which it is called superconducting gap. And that was a key quantity to understand superconductivity. Actually, I recently, or all the way, I tell students that Bardeen-Cooper-Schrieffer got their Nobel Prize almost immediately. But actually, I now checked, it's not very immediately, really. It's in 15 years after discovery, after they suggest this mechanism, they got the Nobel Prize. But I believed it is immediately, but nevertheless, it's still quite fast comparing to modern times, and especially comparing to high temperature superconductivity. But here is interesting why it happens, and this is a story about so-called smoking gun experiment that it was known before that probably phonons are important, but actually that it is phonons that couple superconductors, that couple electron in pairs. Became evident after measuring, accurate measuring of it is tunneling conductivity. So it is tunneling spectra. It is current voltage spectra, current voltage curve characteristic. And if you differentiate it, you get some profile which should be proportional to the density of state for tunnel junction. But if you differentiate it even more, you get some thin structure from this, and this thin structure should represent the spectrum of this in this case spectrum of phonons, and that was compared with the known frequency of phonon spectrum, and therefore it was such very, very robust evidence that it is indeed phonons which couple electrons. And when in 1986 was discovered the new materials, new family of materials was discovered, superconducting cuprates, which we call now high temperature superconductors. Actually, Bednorz and Müller got immediately the Nobel Prize for this, but all people believed that it is quite easy to understand this because the mechanism already known, and it is just you should repeat similar experiment. But it appeared it is much more complicated. And it is this slide represents our result, but it's not only we, but you see this is obtained about more than 20 years after discovery of superconductivity, and I want to, it is quite old result already. I want to stress it here because it is a good example of interaction, of combination of two experiments. It is synchrotron experiment, photoemission spectroscopy, and here is the Fermi surface of cuprates measured by Engel result photoemission spectroscopy, and combination with neutron experiment. And this is the spectrum, the so-called two-particle spectrum, the spectrum of spin excitations measured by inelastic neutron scattering. And these two facilities, we would be happy if our synchrotron, Ukrainian synchrotron community became a synchrotron and neutron community, which we now considering as the most likely the case, and it is usual for other countries also. Here I want to say just without going into details that this formula just represents, let's say, the formula of cuprates, how electronic spectrum of cuprates is built. Here, G is the green function, and it, let's say, here is represents the density of state. So, in simple words, the important quantity which define this in this spectra, you can get from this spectra, which is called quasi-particle self-energy. It is just a certain convolution of the density of state with the spectrum of excitations. Of these excitations, in case of ordinary superconductors, it was phonon spectrum, and now it was shown that it is a spectrum of spin fluctuations. In fact, it's not. I could not say now that this result is completely accepted as in case of phonons, because it is really complex, very complicated electronic structure and complicated experiments, and could be different opinions, and there are different opinions about this, but most of the people now believe that in case of cuprates, it is spin fluctuation spectrum. Danila, I didn't notice when I started. Could you tell me how long should I speak?
We still have 10-15 minutes.
10-15 minutes. Okay. Then I just want to say why actually now I'm going to explain what is this spectra and what is this spectra, ARPA spectra, and how it represents, how it measures the electronic band structure, but also 1 minute to explain why it is difficult for high temperature superconductivity. Just to repeat the experiment, that old experiment which I shown about fingerprints. This is because the complex order parameter, superconducting order parameter. In standard superconductors, the superconducting gap, which represents the superconducting order parameter, it is uniform. And it appeared that here the superconducting order parameter has so-called D-wave symmetry. So it's like D-wave symmetry of the electrons in the Biden at some orbital, at d orbitals. And this means that it is highly anisotropic, and it has maxima and zero at the so-called nodes at the Fermi surface, at the Fermi level over the Fermi surface. And if we measure such quantity as tunneling spectra, all the momenta there are integrated, and but this density of state is shifted by the gap in the spectra. Therefore, it's shifted by the different value of the gap for different momenta, and therefore you have just average. You can't resolve any structure there. And therefore, to make such comparison, you need to compare the spectra with momentum resolution. And this spectra comes from for one particle spectra, for electronic spectra. It comes from angular resolved photoemission experiments, and for two particle spectra from neutrons. So angular resolved photoemission spectroscopy, it is very simple and straightforward tool. You just shine, you just put some photons with certain energy on sample, and this is just photo effect. You measure the kinetic energy of the escaped electrons, excited electrons, and then you just, due to energy conservation rule, you just know the energy, Biden energy of the electron in solid. And this is typical, let's say, XPS spectra. And here is the core levels, and here I zoomed so-called valence band. But if you can resolve the angle of electrons, escaped electrons, photoelectrons, you can get this nice picture which represent actually the electronic band structure. You have angle is easily corresponds to momentum, momentum of electron in solid, and this resolution of momentum, it happens. This picture represents simple analyzer, which is called hemispherical. It is hemispherical analyzer, but here you have electron lens. We just produce the momentum resolution because all the electrons which escape at certain angle focused on the entrance slit at some position. Therefore, you have here the resolution in angle, and that means in momentum. And this hemispherical analyzer gives you a resolution in energy. Therefore, you measure such an image like this. And this image represent you the probability to find electron with certain momentum and certain energy. And here is Fermi level. I will skip actually the explanation how it is. But for quasi two-dimensional materials such as cuprates, you have two momenta. In plane momenta, and this means that electronic band structure looks like this. This is electronic band structure as it should be without interaction, and if we add interaction, we actually measure some distribution, this distribution, and this distribution, this window, we can move in this reciprocal space, just tilting the sample in respect to analyzer. And when we make some angle, we move it in momentum. And we can measure all this area, all this volume, all this reciprocal space, and cut it with maximal energy at the maximal energy, at Fermi energy, and it will be the Fermi surface. And this actually corresponds to explain this smoking gun experiment that would be smoking gun experiment if samples would be better or statistic would be better maybe. But anyway, it shows, I think, this correspondence that this is two particle excitation. This means that electrons from here could go to unoccupied states here, and this is so-called electron susceptibility. And if they sweep the spin, then you have this spin excitation, and this is exactly, you actually can calculate this expected spectrum of spin excitations from known electronic band structure, and you can measure it and see that it is really follows our expectation. Okay, just to summarize briefly my experience about electronic structure in different materials. After cuprates, when we considered that the question of mechanism is settled, we switched to iron-based superconductors, and they are much more complicated in sense of electronic structure. And electronic structure here is you have 5 bands instead of 1, so it is more complicated, but interaction maybe it's not so strong here. But anyway, here it is interesting. We have found how actually empirically the dependence of this multi-band structure, how it relates with superconductivity. I will not focus on it here, but I wanted just to say that just empirically looking at this experiment on electronic band structure on different materials, you can derive some empirical relations and see what is important for superconductivity. And it appears that for superconductivity in these compounds, important the presence of small Fermi surfaces together with large Fermi surfaces. And this is interesting because if we re-examine the case of cuprates, in fact, there is the same situation. Therefore, it seems quite general. But now I want to briefly switch to the case of application. How Fermi surface, geometry of the Fermi surface would be can be important for applications. And this is a story about superconducting qubits. And about importance or how it is prospective, yeah. That superconducting computer you can judge based on the fact that all the giant IT companies like IBM and Google, they built their own superconducting computers. And here, all these complicated devices, it is just cooling system. And actually, superconducting computers, it is a number of qubits, superconducting elements based on Josephson junctions, which are here in vacuum, in THV vacuum, but also at ultra low temperatures. And these temperatures are important because these qubits should be coherent, and coherence is quantum entanglement entangled. But this coherence is very brittle, and therefore it is quite difficult to make many qubits working coherently, because even thermal fluctuation at so low, ultra low temperatures break this coherence easily. And at the moment, it is some old result already, but now not too much more qubits now present. I do not remember the number, but for quantum computing to operate, you need at least 2 orders of magnitude more qubits. And actually, this decoherence problem could be maybe solved just switching to another material, because actually here we use not we, but all the people now. Modern standard is aluminum technology. It is based on aluminum superconductors because aluminum materials, because it's very technological. It's easy to make this contacts, Josephson contacts. But the superconducting gap of aluminum is very low. It is 0.3 milli-electron volts. And even in niobium, it is already an order of magnitude higher, and in high temperature superconductors in even more higher. But this gap is defined, it defines the frequency at which these qubits communicate to each other. Therefore, it would be very interesting to try to use another material with higher gap. And here the example when we tried, actually we were here, it is the first in the world who made Josephson junction between iron-based superconductor and niobium. It is Alexei Kolynyuk did it. He will have talk later in this conference. But actually here we have found that this complex superconducting order parameter is also a problem here, because you have like destructive interference between different signs of the order parameter. And actually this it is called on this characteristics, current voltage characteristic, it is called ICRM. Which define, let's say, this jump multiplied by this jump is critical current IC, and Rn it is normal resistivity. And their product in a normal superconductor is proportional to superconducting gap. But here in this superconductor, it is highly decreased because of this destructive interference. But what is interesting, Alexei have found that if he put thin layer of copper in between niobium and iron-based superconductor, he increased this parameter 40 times. And it was very unexpected because copper is not superconducting, and we expected that maybe we didn't expect such a result, but later we understand it, because copper has such a Fermi surface. It is almost circular Fermi surface, but its projection is projected Fermi surface. It is like a circle, and this circle works like a filter, because if we consider just tunneling of superconducting pairs, they jump from one material from one above material, which is niobium, which is quite homogeneous, let's say, and it jumps to the Fermi surface of iron-based superconductors. And here I show Fermi surface is white, and red and blue, it is the sign of the superconducting order parameter. Therefore, if you have channels, if electron jump here and here, you have this destructive interference. But if you have such a filter, then electron jump only predominantly jump to the Fermi surface of where superconducting order parameter is of one sign, and therefore this parameter is increased, and frequency frequency will be also increased. Okay, this was just an example, and it is one of the result of our project, which was called multi-band electronic structure, funded by National Science Foundation, right? And there is actually another interesting result when we...
sorry for interruption, but time is almost over. So
time is almost over. Okay, I then skip other results. Just want to switch to other projects, because briefly I finish about briefly I show some projects, and this actually work, of course, important, and all the research could not performed without international collaboration. And here is just we recently had very nice project which was called Ukratok with Germany, and important in this project that we have a number of students, scholarship of the students. It is students from Ukraine, not only from Kyiv Academic University. They spent half a year in Germany, and many came back. And also we got some important equipment for Germany, and actually it was very productive. You see the publications from these scholars of this project, and this year publication is Nature publication when they found the new material. This is where topology and superconductivity coexist, and this is very perspective, another solution for this decoherence problem. Now this project is continuation of this project. Let's say it is our German-Ukrainian Center for Quantum Materials, and it is open. I would say for it is open. We are open for collaboration. All people who are interested in investigation of quantum materials are welcome to join. I briefly skip this to say that we have these pages of this project at our site, and you can have here some events, and this was School for Quantum Materials, which lab tours organized by Dresden people. And this is example of equipment. It is magnetron sputtering, which is now prepared to deliver to us. It is one more equipment to us. And where we are? We are here. It is actually an institute based on the Institute of Metal Physics, and we have here also the center of related with Kyiv Academic University. And here is the cryogenic building where our laboratory is located. And I left to the end a few words about synchrotrons. That actually synchrotron experiments, I have experience with synchrotrons, mainly with these 4 synchrotrons, which are Swiss Light Source, BESSY, Electra, and Soleil, but there are many synchrotrons, and now Piotr Pivovarczyk will talk, I think, about Nephews, and I invite all of you to join Nephews project, which gives you opportunity to travel all around the world and to make doing synchrotron measurements. And I have mentioned already briefly that our projects, which we call in general, under general name Light for Ukraine, and this is, it includes as the project of building in Ukraine the synchrotron, building here in Ukraine, but as the first step, and it was supported by our Polish colleague, it is to build at Solaris synchrotron in Poland to build Ukrainian beamline. And about this, I think other talks will be Luke talk and other talks we can hear today. Okay, so thank you for your attention.